Welcome everybody. My presentation today will go over ferrofluid, its application in loudspeakers and its properties. My name is Joachim Schwender and I work for company Ferrotech. The company was founded with ferrofluid and I'll show you quick what we do today. This is the list of our business areas that we have. It's a lot of stuff. Don't worry, I will not bother you with all the details. We're only talking about the department I'm working for, Ferrofluid for many applications, where we have a large part which is dealing with audio applications, loudspeaker. In the beginnings, in the 60s, the company was founded with the invention of ferrofluid. That was new at that time. And originally the idea was to control rocket fuel with some sort of whatever magnetic force into the rocket engine, which didn't turn out to be good or good enough. So the patent and the idea was free to use for any other applications. And that was the point that the company at that time called Ferrofluidics was started. That's what it is like. It's a liquid, but it reacts to magnetic forces. So if you put a magnet next to the liquid, it reacts, as you can see here, with some spikes. So it's a liquid it's black and it has magnetic properties. So I'm going a bit more in detail to the classification and differentiation of the substance itself. If we're talking about magnetic liquids, we know that exist two different types of magnetic liquids. One is solvents and the others are multi-phase systems, which are mixtures of a solid phase and a liquid phase. For the solutions, there exist some salt solutions that react to magnetic forces, but these are only very weak. And the multiphase systems can be differentiated to colloids and mixtures. This is not unimportant because mixtures also exists with magnetic particles, but it's a different kind of material used in different applications. When we talk about ferrofluids, we mean colloids, explicitly colloids. In detail, the difference is mainly is the particle size. When we talk about a colloid, the particle must be very, very small. We're talking about 12 nanometers or below for the particle size of a ferrofluid that we make. Most of our ferrofluids have a particle size of 10 nanometers. When you look at MRF, magnetorheological fluids, that's what the mixture is. The particle size is much larger. We're talking about micrometer size particles. That's a total different thing. In terms of magnetic reaction, the reaction of the salt solutions is very, very weak. For ferrofluids, we'll talk about the saturation magnetization in the order of magnitude of 30 millitesla, more or less. And the MRF can have much higher saturation magnetization up to 0.5 Tesla. If we look to the properties of the ferrofluid, there are several properties like surface properties, magnetic AC properties, viscous properties, thermal properties. You can have force generation and there are also optical properties. But today we are only talking about the properties that are relevant for audio applications. Those are the ones. There are many other applications, mainly that is medical and all kinds of industrial applications. But we are focusing on loudspeaker, of course. But to give you an overview, that's what all possible today. Today we actually do not have any commercial applications for the optical properties. That's, scientific research today. Ferrofluid composition. How do we make a ferrofluid? We start with a carrier liquid. It can be anything that is liquid. For loudspeaker, we use either hydrocarbon oil or a synthetic ester. Other liquids are not used for loudspeakers, but there exists ferrofluids for those liquids. So we have a carrier liquid. What do? We put in a magnetic particle. Not one, many of them. The particles we are talking about could be anything that is magnetic, but in audio applications we use exclusively magnetite as a particle. To make that a ferrofluid, it is very important that we add a surfactant to it. That is a chemical substance that attaches on one end to the particle, and the other end of the substance must be solvable in the specific liquid that is used. So you put it all together, you shake it, and at least that's the principle how you make ferrofluid. But it's not that easy. It's very critical, for example, how well the surface is perfectly covered or not. It's not so easy. Now, to give you a scale on how small these particles are, here is compared to a hair. A human hair is in the order of magnitude of 100 micrometers. That's by far larger than 10 nanometers. A bacteria, it's about 1 micrometer. It's still much larger. Wavelength of light, here I put it, if that's the wavelength of light, that's in scale the particle. So it's much smaller than the wavelength of light. So it's very small. Even a virus is even larger than these particles that we use. And something that is smaller would be something like small molecules, like a DNA or hydrogen atom. You know, it's somewhat smaller than our particles. But as you can see, it's 10 nanometers is really tiny particle. Okay, the relative lifetime of a ferrofluid is here given versus temperature, because the temperature is the main influence on the lifetime of a ferrofluid. Here you can see the different versions and the different families of ferrofluid that we have. Like, these are the very old ones, and these are the newest ones. What you can see here is that it strongly depends on temperature, and the newer generation of ferrofluids have much improved over time. So this is about 3 decades of development of ferrofluids. This is an example of what we publish as the core data of a ferrofluid in our data sheets for audio applications. The main parameter is, of course, the magnetic property, which is measured in saturation magnetization in millitesla. And as you can see, for audio applications, it's always something between 11 and maybe I think the top would be 40 millitesla, but that's the range. The next one is the viscosity. The viscosity is available in different values here. It ranges for this specific type, the L family. It's available from, 60 to 2000 millipascal seconds. In our data sheets, you will find also a pour point. That's the temperature point where it stops flowing. So if you go below this temperature, if you go below this temperature, it will kind of freeze. It doesn't freeze in a way. It just doesn't flow anymore. You will also find the density value and the specific carrier liquid, which is different for every family of ferrofluids. And as I said, we use synthetic esters or synthetic hydrocarbon oils as a carrier liquid. And then you'll find the thermal conductivity value and the thermal expansion coefficient. These values are pretty much the same. They do not vary much for all these ferrofluids for audio applications. So if we talk about aging of ferrofluids, yes, they do age, like everything ages. One point for aging is the evaporation. For a normal liquid, you would define evaporation, it disappears on into the atmosphere. As ferrofluids are more complex liquids, the definition is a little bit different. We look at it until the loss of the carrier liquid thickens the ferrofluid as strong that it doesn't flow anymore. So that happens because the particles do not evaporate. The particles stay. Only the carrier liquid evaporates. So that's a limiting factor for the lifetime of a ferrofluid in an application. The next very important parameter is the colloid stability. You can simply imagine a perfect ferrofluid would be perfectly distributed particles in the liquid, but that's not reality. If you apply a force to it, it's kind of shifted the density within the liquid. So you have areas where the density is higher because you have a higher concentration of particles, and areas where the concentration is lower because it's not equal distributed in the liquid. So the thing is, there is a reversible part of this colloid stability and an irreversible part, which means if you exceed the force that you apply, which could be gravity by a centrifuge, or which could be magnetic forces by a very strong magnet, you would get the particles into such strong contact that they do not dissolve afterwards, and then the ferrofluid is damaged. The colloid stability is different for different ferrofluids. So we have specific ferrofluids which are very high in colloid stability, which can be used in speakers with very high flux densities, like in a compression driver usually you have very high flux densities, and then you cannot choose every possible ferrofluid out of our catalog. You are limited to specific high colloid stability ferrofluids. The normal behavior of this colloid instability is reversible. That means if you apply a normal, not destructive magnetic or force field to the ferrofluid, it will, redistribute equally after putting the forces. Some other aging effects are polymerization of the carrier, oxidation of the surfactant, and oxidation of the particle, but those are not very important. The most important from these here is the polymerization of the carrier. Oxidation of the surfactant is taking part, but the oxidation of the particle is more or less theory, at least for loudspeaker application, because it requires very high temperatures. These aging effects are mostly influenced by, the majority temperature plays the major role for the aging. Chemical environment is not important for loudspeaker. You might have some seawater vapor or something like that, but that's it. Or you might have, during the production, you might have some vapor from glues that may impact it. But for normal operation, that doesn't play a role. Humidity in operation is maybe important as soon as it's getting condensing humidity. Humidity that it's non-condensing is not a problem at all. As I already mentioned, the colloid stability must be chosen related to the flux density that you have in your speaker. The most important, as I said, is the temperature profile. If you have very high temperature, you will reduce the lifetime. That's what you already have seen in the 2 slides before, where the accelerated lifetime was presented. Where does it go? For most of the applications, the ferrofluid is applied inside and outside of the voice coil in the voice coil gap. There are very special applications where you put, for example, only in the inner side of the voice coil the ferrofluid. But that's exotic, I would say. That's the point where you apply ferrofluid. And of course, we are only talking about electrodynamic speakers, not electrostatic, plasma, whatsoever else. The effects. What does that do if I put ferrofluid in such a speaker? The ferrofluid has a 4-time increased thermal conductivity compared to air. That means, first of all, you get increased power handling. The thermal robustness gets higher, and by pulling the heat away from the voice coil, you get a lower operating temperature, at least for the voice coil. And as a side effect of the lower temperature, of course, the power compression is reduced of the speaker. The second thing is you provide a centering force to the voice coil, which is actually a static force, which is created by the fact that you always have a magnetic field gradient towards the center, and the ferrofluid is always attracted in direction of the gradient field. So thereby the voice coil is displaced equally within the gap. And that's creating this centering force, which is helpful maybe for easing the manufacturing process, or is also possible to create a spiderless woofer. The ferrofluid in the voice coil gap reduces lateral movement because this is a strong damping of any rocking or lateral movement of the voice coil in the gap. This might reduce distortion, those ones that are related to these motion modes. What you get if you put it in this place here is you create a hermetic seal. So without ferrofluid, of course, you can have air going in and out. With ferrofluid, that's completely sealed, which can be, protection seal for harsh environment, for increases robustness. It may smoothen the frequency response, and it reduces all the airflow from the inside of these cavities to the outside, which may cause noise during operation. So it can reduce the noise that is created by this flow. What it also does, it requires a proper venting, because if you have at least if you have a long stroke system, you certainly get a pressure built up into these cavities. Therefore, these cavities must be vented properly. That's very important in the design of a speaker with ferrofluid. The ferrofluid acts like a lubricant, which can, in case of an overload, prevent failures due to direct contact of the voice coil to the pole plates. And this way it can reduce field failures and it can increase the operating lifetime. Another effect is directly related to the magnetic properties of the ferrofluid is you increase the flux density in the voice coil gap, and thereby you increase the efficiency. This opens the opportunity to reduce possibly the width of the gap or the magnet size, or you get an improved efficiency. Those are the possibilities. With putting ferrofluid in the gap, you of course get an increased damping because the viscosity of the ferrofluid is higher than of the viscosity of air. Therefore you get a damping, which you can vary by choosing a proper viscosity of the ferrofluid. We provide many viscosities as I've already shown in the example of the data sheet. And it's part of the design process to choose the proper one for the required damping. The viscosity effect here, again, that's at the resonance peak, which is shown here without ferrofluid. You get a very high peak. With a low viscosity, it's lowered, and the higher your viscosity is, the lower is the peak of the resonance frequency. One important thing to mention is that this viscosity is strongly dependent on the temperature of the ferrofluid. So with a variation of temperature, you get a variation in this damping. That must be also, taken into consideration during the design of the speaker. To give you a scale for what viscosity means, air, for example, is very thin material. It has a very, very low viscosity. Water is a liquid with also a fairly low viscosity. You can easily remind because it's a value of 1 millipascal seconds. So what you probably know from kitchen is something like olive oil, which is in the order of magnitude of 100 millipascal seconds. You've already seen probably some motor oil, which is thicker, and you're used to, for example, honey, which is very thick. That would be something like 10,000 millipascal seconds. And ferrofluids we can provide, or ferrofluids for audio applications, they vary in this range here between starting from 25 millipascal seconds up to 10,000 are available for audio. Here I come back to the thermal effects, which is one of them is the thermal compression. And what you see here is a speaker example where we apply power for 30 seconds and look to what result is the temperature, one time without ferrofluid and one time with ferrofluid. And as I already mentioned, the temperature increase is slower with ferrofluid compared to without ferrofluid. Or if you look at it in a larger time scale, the increase comes to saturation state where all the temperatures are in an equilibrium between inputting power and dissipating power. But still at the end of this, or probably end of this process, the temperature with ferrofluid is significantly below the temperature without ferrofluid. And that means the increase of the resistance of the voice coil is less compared to what you have if the temperature is higher, of course. If you look to the spectrum of such an example, here is one example where the power compression, that means the loss of the efficiency due to the increased heat of the voice coil, is very dramatic here in the upper frequency area. And if you put ferrofluid in that, I forgot to mention this is right after start of the test, and this is after 45 minutes. And if you put ferrofluid in that, you see that it's still a drop, but it's much more equal and it's less. So the power compression is reduced. That means at the end you have a more efficient speaker with ferrofluid than without ferrofluid. If you look to that as power linearity, that's in this example here, if you have a speaker with efficiency of 90 dBs, for example, you calculate it at a rating of 50 watts to 170 dB, but that's not what you get. What you get without ferrofluid is this here. You get a drop because of the increased temperature of the voice coil. The resistance increases, and therefore you get less output power, which ends up in this example like 101 dB. If you put ferrofluid in it, the drop is less, and the efficiency ends up to, or the SPL ends up to 105 dB, which is much better than without ferrofluid. I already mentioned this effect of the ferrofluid. Here is more in detail. The model that I look at is here, this the inner pole, the outer pole, and that's the voice coil. And these are the this is the geometry of it. And the static force can even be calculated by this formula, which is, I think, very simple. You have a material property, which is the saturation magnetization of the material, of the ferrofluid. You have a second, it's a magnetic design property. This is the field strength that you create with your magnet in your system. And the second one is a gap geometry. So those are the influence parameters to the parameter K, which is nothing but a spring constant. That means how much deflection of the voice coil do I get if I apply certain force to it. And those are the parameters that you can influence this. This force isn't, if you look at it, not very great, but it is as used for the manufacturing process, it's useful. And this formula, as this measurement shows, works at least for small displacement. So it's I'd say a first order model that works. This is how it looks like if you apply ferrofluid to a gap where you have, as you can see here, a displaced voice coil here. And if we put ferrofluid in it, oh, sorry, oh. Okay, sorry, once more. If you look at the position of the voice coil while the ferrofluid is dropping in, you see that it's moving to the center. And at the end, it's almost perfectly centered just by putting the ferrofluid in it. And that's the effect. The ferrofluid in a speaker is not a one-size-fits-all solution. There are several things that must be considered during the design phase of the loudspeaker, like any other component of the loudspeaker too, like a diaphragm or magnet or pole plate, anything. First is the base type. If it's a hydrocarbon or an ester, this can be chosen with respect to the humidity tolerance, as the hydrocarbons tend to be more tolerant to humidity. If your application has to deal with humidity, like a speaker in a stadium or on a ship or something, you'd better choose a hydrocarbon and not an ester, as an example. The viscosity must be chosen based on the resonance frequency, the maximum excursion, and the applied power, and of course the damping goal. If you want damp or if you don't want to damp. Like in a woofer you would normally not want to damp, so you choose a very low viscosity material for a woofer. In a tweeter you might want to damp, and therefore you can choose a higher viscosity material to get the proper damping that you want. The saturation magnetization is a property that you must choose depending on the excursion of the voice coil and the flux density that you have in your gap. So that means the higher your excursion, the higher the excursion of the voice coil is, the higher the saturation magnetization should be. And the stronger your magnetic field, the smaller your saturation magnetization can be. So why would you choose a smaller saturation magnetization? There is a reason for that, because saturation magnetization is related to the content of particles in the liquid. So a high saturation magnetization ferrofluid will have more particles per volume than a low saturation magnetization material, which then means if you have a loss of carrier liquid over time by the carrier liquid, the high saturation magnetization material will react earlier to that loss of carrier liquid. So if you're able to choose a low saturation magnetization ferrofluid in your application, it'll probably last longer in your application. The colloid stability, as I already mentioned, must match to the flux density that you have. And an important point during the design is the compatibility testing. As the ferrofluid is in contact with different materials, the glues, the collar material and so on, it must be made sure that this is compatible with all the materials that are in contact with. Otherwise it could, if you just put it into any speaker, it could dissolve the glue or something like that. That is nothing you want to have. Therefore, testing for compatibility is very, very important. The filling volume must also be determined properly. And as I already mentioned, cavities venting is very important. And all this must be properly designed into the speaker. The filling volume is a very simple process, because at the end you just calculate the volume that you have here, which is given here by all these diameters. I forgot to mention that's the inner pole, that's of the top pole, that's the outer pole, that's the voice coil, of course, with the wire windings, and that's the ferrofluid that fills the gap. So now we have, height of the top plate, several diameters, and you get a simple formula where you have the height, that's the geometry. You have a circle, of course, therefore it's a cylinder calculation, very easy, and that is just a compensation factor for the meniscus that you get. So we tend to do a little bit overfilling. That's enough to provide to determine the filling volume, and that's how we do it. We let our customers fill in this loudspeaker information sheet. Here you can see this formula. This is 3.5 times whatsoever. That's exactly pi times 1.1, 10% on top of it. And as I said, we let our customer fill that in, and from this we can do a first guess which would be the first candidate for testing the ferrofluid into the application. Now I'm coming to the impact of the magnetic circuit. What we see here is the magnetization curve of 3 different ferrofluids, and on the other hand here the susceptibility curves of the ferrofluid. Let's first look to the magnetization curve. That's the more interesting one. 3 different ferrofluids. The curves look very similar, just different scale, and that has a reason, because we always use the same particles. And as I said, the saturation magnetization is the main parameter, and as you can see here, this is the S10, which has higher saturation magnetization than these other types which are here. So the level that you get here is just correlated to the saturation magnetization. That's the flat part of this curve. And as you are in a speaker application always in an area where this curve is very, very flat, you can consider it just as a constant number, the saturation magnetization. You don't need to look at the whole magnetization curve. So what does it do in your magnetic circuit in your speaker? The normal thing that you have in your gap is the linear behavior between the magnetic field and the flux density, right? You only have this parameter. If you look to the ferrofluid, that's this curve here in principle, and that's contributing to the flux density in your gap. In total, it adds up, and you get a curve like this. At the end, what you get in your magnetic circuit is just an increase of your magnetic flux by just the magnetic saturation value of the ferrofluid. It looks like this. You have the same formula here, just plus this constant value. Very simple. It's precise enough for this application, of course. As an example, if you have a flux density of 1 Tesla in your gap, you add a ferrofluid with 40 millitesla to your gap, you end up with 1.04 Tesla. That's it. Very simple. For the efficiency, that would mean, as the B square goes to the efficiency, it's like 8%. That's the gross efficiency increase. Another very important point for the design of a ferrofluid in a loudspeaker is capillary migration. Because the capillary forces that you have are much greater than any magnetic forces that you can apply to a ferrofluid. As capillary forces go stronger as narrow with a gap of something getting smaller. So with very small gaps, you can get very, very high capillary pressures. As you can see here in this example, in the upper you have a sample sitting into ferrofluid, which is properly treated with epoxy sealing, which prevents this capillary migration into the collar here. If you don't do that, that's what you get after a certain time. Here in the beginning, after 8 hours, you already see something, and at the end, you get this capillary migration, which sucks out the ferrofluid from where it should be to areas where you don't want to have it. That's our product development history over the last decades. It started in the early days with this type of ferrofluid, then had some other types of ferrofluid with each time different chemistry. Some of them are discontinued products as of today, like the 2000 series is no more available. 1000 series is discontinued. And right now we are about to discontinue some specific types of ferrofluid. And in this case, The reason why we do that is because one of the components is no more available on the market. You cannot buy it anymore. Therefore, we have to discontinue it. And that means for us, we are looking for something that substitutes it and can replace it. That's what we did, or what we are in progress of doing this with this specific types. The whole product in development over the time led to improved lifetime, improved stability, colloid stability series, especially the CD series is our ferrofluid series with the highest colloid stability that we have. And the temperature resistance of the newest ferrofluids have improved a lot over the older series that we had in the past. At Ferrotec we have a global risk management which turned out to be very, very important nowadays for production. Ferrotec itself had also an issue with the Fukushima accident where we lost one production facility in Japan, which was not fluid related, was seals related, but it showed that global risk management is something very important because also our customers are a request from us to make sure that we are not a single point of failure in case of anything that can happen. What we do to control all this is right now we have our manufacturing is ISO 9001 certified. Our quality controls history is much longer than we are certified. We have, from every batch that we have ever manufactured, we have retaining samples and all documentation. So, as I already said, the disaster resilience is given by the fact that we have two manufacturing sites, one in Japan and one in the United States, which are all capable of produce any of the ferrofluids that we have. That's currently not the case because currently specific types are done in Japan, other types are done in the United States, but that could be potentially shifted very quickly. We have a large buffer stock of raw materials. We have some materials on stock which are a buffer stock for us, for our production, for like 10 years that we have on stock to really make sure we can deliver. As the major part of our customers is automotive, they really want to make sure you must deliver. It's very important. And that's how we do that. Another thing is we cooperate strictly with very reliable suppliers, and we do not change suppliers just because, little cheaper or something. That doesn't work that way. If we ever change a supplier, that means for us we change the product, and then it's also we create a replacement product, even if it's a similar product from a different supplier or the same product from a different supplier. We would change the nomination of the product that we have. Ferrotec promotes strongly employee loyalty. We have employees which are at Ferrotec for a very long time. Like me, I'm doing this for 30 years now. And at the manufacturing side, we have a very high level of admission control. That's more or less standard for such a production today. As I already mentioned earlier, our life cycle management is up since the beginning. And this comes from semiconductor industry where that's called copy exact, which means you are not allowed to change anything. You cannot even change the smallest part or production method or anything in your production unless you notify the client. And that's what we did from the beginning. And that's also a very, very strong part of our quality policy that we do. Now at the end I will show you how that looks like. It's not so easy to show that because, as you can see here, the ferrofluid in action is always hidden by, several things. So I cut off this speaker, and this is a 1,000 frames per second slow motion. So even with this excursion, you see that in principle the ferrofluid is well retained in the gap, even with the excursion of this loudspeaker. So don't worry, this looks terrible here because all the surrounding is gone and the spider is cut off, where as a result you can also see rocking modes which are induced by this. But the thing is, that's the only way to look at the ferrofluid in action. And right. So that's the end of my presentation. Are there any questions?
Why is it not more present in the speaker?
I would say there is not a single manufacturer in the world that doesn't know us. Most manufacturers do use ferrofluid, but not in every model. First of all, it's very common in tweeters, and it's most common in automotive tweeters. The thing is, because their main issue is the speaker must be light and small. And the use of ferrofluid allows them to apply a lot of more power than without ferrofluid. So the dimension of the speaker at the end are smaller with ferrofluid, and therefore almost all of them use ferrofluid in a car speaker. Mostly you find ferrofluid in it. In other speakers, the benefit you gain is not as much, like in a woofer typically, because a woofer has a longer excursion. Therefore, the ferrofluid cools only a part of the voice coil and not all the voice coil. Like in a tweeter, you have an underhung design, for example, where you cool with the ferrofluid 100% of the surface. With a woofer, that's not possible because you have excursion outside the field, and therefore the reduction of the cooling effect is less in a woofer than in a tweeter. And therefore, it's not that common. And on the other hand, in a woofer, you usually need a much higher volume of ferrofluid than in a tweeter. So it's also more a cost issue, or the relation between cost and what you gain is not as attractive as putting into a tweeter. That's it. Thank you.